Hello everyone, and welcome. My name's Tyler. I'm an application engineer here with Capture 3D. Today we're going to talk about the basics of GD&T and the use of GD&T in the GOM Inspect software. Before we begin, a couple of things. This presentation will focus on the ASME Y14.5 GD&T standard, not the ISO 1101 family of standards. These standards do have some differences, even though there is quite a bit of stuff in common. I'm also providing a link to download our free inspection software, GOM Inspect, as well as the starting project file so you can follow along with the examples. So what is GD&T? GD&T stands for Geometrical Dimensioning and Tolerancing. GD&T is designed to unambiguously describe the part using a rigorously defined standard. It describes how the part is to be both manufactured and inspected, and it describes the part based on the function or assembly conditions of the part. GD&T callouts are broken into a couple of different areas. Generally speaking, you start with datums, then you define things with sizes. From there, you refine the requirements with form tolerances, orientation tolerances, location tolerances, and lastly, profile and runout tolerances, which kind of do a little bit of orientation and form. GD&T has some significant advantages. For starters, each characteristic is unique. There is a defined way that everything is supposed to be measured, as opposed to the ambiguous dimensions you might see on a print. With careful tolerancing, it's possible to avoid a phenomenon called tolerance stack-up, where multiple features at their largest or smallest acceptable size contribute to a part that won't actually work for production, even if it passes the inspection requirements. Traditional location-tolerant zones are square in shape due to their plus-minus nature. GD&T location-tolerant zones are round, leading to a 57% increase in the tolerance zone, meaning that more parts which work for production purposes are accepted by QA. And GD&T tolerant zones define the size, location, orientation, and form of a feature based on the function that feature is supposed to fulfill. There are a couple of disadvantages to GD&T, the first being complexity. The GD&T standard is more than 200 pages long with tons of example cases and rules, and while you can always look up your specific application, that can end up being a barrier to use. The good news is that some of this knowledge can be built into CAD and inspection software, reducing the need for some of this specialized knowledge. Okay, that was a whole lot of words. Let's take a look at a really basic example here. I have a really simple assembly. The gray block is intended to be assembled to this green block, and this yellow pin is designed to pin the two of these together. I want the gray block to contact the green block on 3 faces, and there should be no gaps between the green and gray blocks. Then our yellow pin should fit through the holes in both the green and gray block. Today we're going to be dimensioning this gray block using GD&T such that it meets these functional requirements. The basic idea behind GD&T is that instead of having plus-minus tolerances, each feature is defined by a tolerant zone. Depending on the GD&T tolerance, this zone can be moved and rotated. The goal is to minimize the size of this tolerant zone while fitting all the points of our surface inside. If we can fit all of the points of our surface inside and the size of the tolerant zone needed to do this is less than the requirement, the part is acceptable. Using GOM Inspect software, it's possible to both calculate the resulting value of the check, the size of the tolerance zone needed to enclose all of the surface, and visualize it as a color map to show where our high spots and where our low spots are, making it much easier to troubleshoot manufacturing. The shape of the tolerance zone is defined by the specific GD&T check. Common tolerance zones include 2 parallel lines or planes, a circle or a cylinder, a set of concentric circles or cylinders. Occasionally you'll see a spherical tolerance zone, and then for freeform surfaces, it will be a set of parallel freeform surfaces equidistant from each other. Datums are a very important concept in GD&T. Datums act as the basis for measurement. To describe the location of something, we usually give a distance from something else. In this example, we have a hole that is 40 millimeters away from datum B and 75 millimeters away from datum C. It is possible to combine multiple elements into a common datum. It's also possible to take several elements and combine them into what's called a datum system. Datum systems are arranged in a hierarchy, meaning that the order is important. Your primary datum will constrain all of the degrees of freedom that it can. The secondary datum will constrain as many remaining degrees of freedom as it can, and your tertiary datum will fully constrain your part. Any geometric element can be made into a datum. However, if you're going to use a freeform surface as a GD&T datum, I strongly recommend you make it the last element or your tertiary datum. Freeform surfaces can constrain all 6 degrees of freedom by themselves, meaning that it would be the only datum that would be necessary. We'll pop over to the software now and I'll show you some datums. We're going to start by creating the datums we need on the gray block. So I'm going to make it exclusively visible and temporarily hide this green block and the yellow pin. To make my gray block exclusively visible, what I'm going to do is select it and then hit the E key on my keyboard to make it exclusively visible. Now I can create the needed datums and datum systems on this part. To do that, I can either click on the magnifying glass icon here in the toolbar to open our iInspect wheel, or I can control right-click anywhere in the 3D view to have it appear underneath my mouse. This icon right down here, this is our GD&T Quick Create tool, and I'm going to select Create Datum System. The datum system I'm going to create is ABC. And to create datum A, I'm going to click on this icon right here for Create Fitting Element. Datum A is going to be the plane on the bottom side of this part, so I'll control click on that, right click when finished, and we'll go ahead and leave that with the name of datum A, because that's what we're going to call it. Datum B is this longer side on the back of the part here, so once again I'll click that Create Fitting Element icon, and control click on that, right click when finished, and once more for datum C, which is going to be this surface right here. So create fitting element, control click, and right click when finished to name it datum C. Computation mode GD&T is correct, so we'll go ahead and hit create and close. So now I've got my datum system created and my 3 datum features have been created. To make this a little less cluttered, what I'm going to do is select the datum system, hit the tab key on my keyboard, and under display, I'm going to show only coordinate system so those purple planes aren't cluttering our view. I need to create a second datum system that we'll use later, the datum system AB. So to do that, I can go back to my quick GD&T create datum system. In this case, because A and B already exist, I don't need to go to this create fitting element. Instead, I can just rename my coordinate system and select A and B from the drop down here. We'll go ahead and hit create close. That'll create that datum system. And just like last time, I'll hit the tab key and show only coordinate system so those purple planes aren't cluttering my view. One of the most important concepts in the ASME GD&T standard is called the envelope principle. Let's take a look at a simple example. A cylinder is defined on a drawing as being 20 millimeters in diameter nominally, with a lower tolerance of -1 millimeter and an upper tolerance of +1 millimeter. What this means is that we can construct 2 concentric cylinders, one 21 millimeters in diameter, the largest acceptable size, and another 19 millimeters in diameter, the smallest acceptable size. You see those cylinders in the picture here as translucent blue. These cylinders form the envelope that the surface of the actual cylinder must never violate. The actual surface of our real cylinder is shown here in gray. This cylinder is not smooth or straight, but the entire surface is inside of the tolerance zone dictated by the design engineer, so it passes the size check. The more official GD&T way of saying this is that the total deviation of the size and form cannot exceed the total size of the tolerance of the feature. Or at maximum material condition, you must have perfect form. Distances sound simple until you realize that an actual part will never be perfect. These imperfections mean that different measuring tools and techniques will give different answers. Look at the 30.2 millimeter dimension on the right-hand side of the part. It seems simple enough, but when our actual imperfect part is produced, we can have 7 or more different ways of measuring this dimension, all of which will give us a different measurement. These imperfections are exaggerated here, but for parts with tight tolerances, your measurement technique and tools may incorrectly classify the part. However, once we add GD&T to the mix, we remove any of that ambiguity. We now have a clear and defined tolerance zones and the locations for these features. With the ambiguity removed, there's only one correct way to measure this part. Okay, now that we've got our datums all created, what we're going to do now is measure the size of this part. Specifically, we're going to measure its length, its width, and the diameter of this hole right here. So to make things a little bit easier, I'm going to make my part exclusively visible. So once again, I'll just select my part and hit the E key to make it exclusively visible. And now I can use my quick GD&T creation, and I'm going to go to Dimension Envelope Principle. With that selected, I can Control-click on the first plane, Control-click on the second plane, and then right-click when finished. We'll leave the tolerance at plus or minus 0.5 millimeter. Go ahead and hit OK. And that's measured the overall width of the part. Notice that we were given 2 numbers for this, not 1. There is a minimum distance across these 2 planes and a maximum distance across these 2 planes. And that's what you're seeing here. The software is telling you the smallest distance and the largest distance, because remember, no area of this may exceed the tolerance zone as set out in the print. I'm going to do the same thing again, but this time on the width. So with nothing selected, I'll go to my quick GD&T creation and check the dimension envelope principle. And once again, Control-click on this side, Control-click on the opposite side, right-click when finished, and that gives us the dimension there as well. We'll leave that tolerance at plus or minus 0.5 millimeter. The last thing we'd like to check is the size of the hole here in the middle. So once again, with nothing selected, we'll go to our dimension envelope principle, and we'll Control-click on that cylinder there, right-click when finished, and we'll leave the tolerance at plus or minus 0.5 millimeter, and now you can see the results. Again, 2 numbers. There is an inner boundary and an outer boundary here, and you're seeing both of those values. All right, that takes care of sizes. Back to the presentation. Now we're going to talk in a little bit of detail about form tolerances. There are a few form tolerances that will help us in our journey to dimension the gray block. Our gray block makes contact with the green block on 3 sides, and we don't want there to be a gap between them. One way we could control this is to apply a flatness check to these surfaces. Flatness measures the deviation from a perfect plane. The tolerance zone here is 2 parallel planes, and the distance between these planes is set by the tolerance. We're allowed to move and rotate this tolerance zone any way we need to enclose all of our surface. If it's possible to enclose all of our surface, our feature passes. As a bonus, flatness also controls surface straightness of your plane. Please note that flatness is not the same as RA surface finish. While a really bad surface finish can impact flatness, these are typically measured on very different scales. We have a hole in our gray block, and to make sure that the pin is going to assemble through it, we need to make sure that the hole is not out of round or shaped like a macaroni noodle. One of the ways we're going to control this is by using a cylindricity callout. The tolerance zone for cylindricity is 2 concentric cylinders, and the difference in the radius of these cylinders is equal to the size of the tolerance zone. We're allowed to move, rotate, and even grow and shrink these concentric cylinders any way we need to totally enclose our surface. If we can totally enclose the surface of our cylinder, then it passes. As a bonus, cylindricity controls surface straightness of your cylinder. You can see here that if the cylinder was badly macaronied, it would violate the tolerance zone. As a general rule, cylindricity tolerances need to be tighter than the diameter tolerance. Remember our envelope principle from earlier? The envelope which controls the size of your cylinder also controls the cylindricity to the same amount. This means that cylindricity should be a further refinement to size. While cylindricity controls surface straightness, as a bonus, I also want to control the straightness of the axis of my feature, and that is where DML, or derived median line straightness, comes in. The tolerance zone for this is a single cylinder in which the derived axis must lie. Let's look into how we calculate this axis. We start with the surface of our cylinder. We then cut a section out of this cylinder, seen here. That's the section right there. And we fit a circle to that section. That circle is shown in green here. We also keep track of the center point of that circle, shown in black. What we then do is we move our plane back slightly and start this process all over again. We do this down the entire length of the cylinder and connect all of the circle center points together in a curve. Then we check to see if that resulting curve is inside of the tolerance zone. All right, we're going to check the form tolerances. In this case, I'm going to check the flatness of datums A, B, and C, and I'm going to check the derived median line straightness of cylinder 1. Now, because these elements already exist, there's no sense in creating a brand new plane on the bottom, or this side over here, or this side over here, in order to be able to measure those features. So what I'm going to do is select my cylinder, Control select my CAD, and then hit the E key, so they're the only things I see. And I'll go to my Explorer here under Block, Geometries, Planes, and I will bring out planes A, B, and C by clicking on the icon here to make them visible. To check the flatness of A, B, and C, I'm going to do them all at the same time since they're going to have the same tolerance. So I'll select A, B, and C by just holding the Control key and clicking all of them, and then come to my GD&T checks and add a flatness check. And that'll be flatness to within 0.5 millimeter. Go ahead and hit OK. Notice that B and C pass this check, but datum A does not pass this check. We'll come back to that in a second. For cylinder 1, I can select it and then add a straightness callout. Notice here the tolerance zone is on the surface, the outer edge of the part. This would be surface straightness of the cylinder. What I want to measure is the derived median line straightness. So I'm going to change this tolerance zone type from planar to circular, and that brings the tolerance zone into the middle there. We'll leave that at 0.5 millimeter, and we'll go ahead and hit OK. We can see that's quite straight as well. Let's take a look at what's going on with plane A. I'm going to select all of these guys, make them invisible, and let's see if we can figure out what's going on with plane A and why it's so badly out of flat. You may remember earlier I mentioned that it's possible to visualize where the high and low spots are on a surface once you have full 3D scan data, and our software allows you to do that very easily. What I'm going to do is select the check, not the plane, but the check item here, hit the Tab key on my keyboard, and under Display, make sure I select Show Color Deviation Representation. I'm also going to hide the tolerance zone because that's going to make things a little bit easier to see. Now all I have to do is separate the check for the plane so I can make the plane invisible. So I'm just going to choose Visualization Checks Separated. That way I can make the plane invisible, I can make the CAD invisible, I can bring out my mesh. And now we can see we've got some very low spots here and kind of a low spot here. Anywhere you see color in the software, it's possible to add a deviation label. So by selecting this, I can go to my checks deviation label, and I can Control click to add a deviation label anywhere I'd like on the surface. So we can see those very low spots along with that very high spot there. And the difference between them is giving us our substantial value here. So you can see that it lifted up here in the corners, and that makes sense. This is a 3D printed part, and if our bed adhesion wasn't particularly good, the corners would lift up during the printing process. And that also explains the sort of wrinkling you've got on the side here, as all that plastic was just kind of piled on as the printer went over it. So up until now, we've controlled form and size of the features on our part, but now we need to make sure that all of those features are oriented in the correct way to each other. As an example, we can go back to our gray block. We've got that right corner in the back that needs to mate with those 3 planes on the green block. If our gray block's planes aren't perpendicular to each other, well, we're going to run into an issue when we try to assemble them. This section is actually going to be pretty short because there's really only one orientation tolerance, asterisk, we'll get to that in a second. The first orientation tolerance we're going to talk about is called angularity. The tolerance zone here depends on the feature type. It's either 2 parallel planes or 1 cylinder. When it's parallel planes, the distance between those planes is the tolerance. When it's a cylinder, the diameter of that cylinder is the tolerance. The important thing here is that the tolerance zone must be oriented to some datum, and the orientation of this tolerance zone to the datum will be specified in the drawing. Here you can see it's 35 degrees. We're allowed to translate this tolerance zone and rotate it so long as it remains correctly oriented to the datum. Just like all of our GD&T checks up to this point, we're trying to enclose all of the points of the surface. If they all fit inside the tolerance zone, it passes. It shouldn't come as much of a surprise that you need at least 1 datum for this callout, since we have to measure the angle of the feature relative to something else. And here's where that asterisk comes back. There are two other orientation tolerances, but they're really just special cases of angularity. Parallelism is angularity where the angle is 0, and perpendicularity is angularity where the angle is 90. Everything else is exactly the same. What we're going to check now is the perpendicularity of plane B to plane A. We're going to check the perpendicularity of C, and we're also going to check the perpendicularity of cylinder 1. Let's start with plane B. I want to check its perpendicularity to plane A to make sure that this edge here is a nice right angle. So with plane B selected, I can go to my GD&T inspections and add a perpendicularity callout. In this case, my datum system is really just going to be one feature, datum A, and we'll leave the tolerance zone there at 0.5 millimeter. Make sure your computation standard is set to ASME Y14.5 or you will get a different result. Go ahead and hit OK there. Plane C, we could check its perpendicularity to A, but that wouldn't necessarily guarantee that this corner in the bottom here was a nice right corner like it's supposed to be, where three planes all intersect each other in a mutual perpendicular relationship. So what I'm going to do instead is I'm going to check C to both A and B simultaneously by adding a perpendicularity check. And in this case, I'm going to use the datum system AB we created earlier. Leave the tolerance zone there at 0.5 millimeter. We'll go ahead and hit OK. Once again, we can see that this is non-conforming. This is a quite large deviation. And whenever we see that, we can of course visualize that to see what's going on with this surface. So once again, we'll select the check, hit the tab key, and under display, we'll do show color deviation representation, and I'll hide the tolerance zone to make things a little bit easier to see. We can do our checks separated again, and we can hide our plane. Hide our flatness check and hide our plane there. And once we hide our CAD, we can actually see what's going on with our mesh here. You can see that we've got a high spot up in this corner and a low spot down in this corner. And again, whenever we see color in the software, we can add a deviation label to that. We can see the high and the low spot there. So significant deviation across this surface. It's not nearly as square as it should be. The last thing we're going to check is the perpendicularity of cylinder 1 to datum plane A. So with cylinder 1 selected, I'll go ahead and add a perpendicularity check. And in this case, we're going to do perpendicular to just A. And the tolerance zone here is going to be circular. You'll see the planar here only constructs two planes. It doesn't constrain it in all degrees of freedom. What we want is a circular tolerance zone to ensure that it's constrained properly. We'll leave the tolerance zone there at 0.5 millimeter. Continuing along on our journey to dimension our gray block, we need to make sure that the hole is in the correct place. Location tolerances will allow us to do this. Please note that in the most recent GD&T standard, concentricity and symmetry have been removed. This leaves only position and surface profile to control location of features. We'll be covering surface profile in a later section. The tolerance zone for position is two parallel planes or a single cylinder. In the case of the planes, the distance between the planes is set by the tolerance. For the cylinder, the diameter of the cylinder is set by the tolerance. The important thing to keep in mind here is that the tolerance zone must be oriented and located from at least one datum. You can use more though if needed. The picture off to the right is a little confusing at first blush, but let's break it down into its component pieces. We first start with the drawing and the datums. We can see that this hole is located 40 millimeters away from datum B and 75 millimeters away from datum C. Using this information and the tolerance specified in the drawing, we can construct our tolerance zone, shown here in blue. The tolerance zone is located based on the datums B and C, and its size is dictated by the tolerance set in the drawing. What you see here in white is the actual surface of our cylinder. This is the actual data on the real part we've manufactured. We're going to use it to construct a fitting element. The cylinder shown here in green is constructed using the actual surface data. In this case, it's the smallest cylinder that will physically fit inside the white data. We call this a maximum inscribed cylinder. The axis of our fitting cylinder is shown here in black. For the position tolerance to pass, the axis of this fitting cylinder must be completely inside the tolerance zone in blue. All right, the last thing we're going to check on this part is the position of cylinder 1. In this case, we're going to check it to the position of ABC. So what we're going to do is go to our GD&T check and check position. Our datum system is going to be ABC. Our tolerance zone is once again going to be circular. We want to make sure that we've got a circular tolerance zone that fully constrains our part. We'll leave the tolerance at 0.5 millimeter. Standard's going to be ASME Y14.5. We'll go ahead and hit OK. And we can see that our position is just out of spec here. When it comes to a feature of size, we have another modifier that we can apply, namely material conditions. On the left, we have the hole on the gray block while it's sitting on top of the green block. This hole in our gray block is at the smallest allowable size. As you can see, any error in this position of the feature will mean that the yellow pin can't possibly assemble. On the right, we have the same hole, but we're going to make it larger. As you can see, as the hole gets bigger, we can tolerate more error in the position of the hole and everything will still assemble correctly. This is the idea behind maximum material condition. We specify the position required at a hole's smallest size or a pin's largest size, and we get a bonus tolerance based on the size deviation from this. So you remember that our position tolerance calculated just out of spec, but you may remember from earlier that our hole is actually ever so slightly oversized. What this means is that we can actually take advantage of an MMC check here. So what I'm going to do is with this selected, I can right-click, edit creation parameters, and I can add an MMC tolerance here, or material requirement tolerance. So I'll switch that to MMR. Maximum material requirement is what they call it in the ISO standard. So the label will say MMR, but it's actually MMC in the ASME standard. They just didn't want to add both MMR and MMC when they're functionally the same in both standards. Leave the tolerance zone at 0.5 millimeter and hit OK. And now you see that we pass. Our position went from unacceptable to acceptable simply because our hole was slightly larger than it was supposed to be. We picked up a bonus tolerance there, and that allowed this GD&T position check to pass. By the way, if you're using the free version of the software and you tried that, you might not be able to edit the creation parameters. What you can always do is just add another position check. Just come to your GD&T Quick Create, you can add a second position check. And that way you can have position with and without MMC displayed on there. Since our part is very simple, we will not need to add any profile or runout tolerances to it, but I wanted to touch on them briefly before moving on. Surface profile is the Swiss Army knife of GD&T tolerances. Depending on the feature and the datum structure, it can control size, location, orientation, and form of any feature. The tolerance zone for surface profile is two freeform surfaces with a constant distance between them. The shape of these freeform surfaces is dictated by the nominal surface. You can think of each side of the tolerance zone as a clone of the CAD surface. Without any datums, surface profile only controls the form of a surface. Adding datums will allow it to control form, location, orientation, and size based on what datums you use. Surface profile is an extremely powerful tool, but it must be used correctly. Surface profile inspections can be extremely computationally intensive to calculate and perform. What this means is that you should prefer to use standard form tolerances like flatness, cylindricity, etc. whenever you're able to, and only use surface profile when it's really needed. Runout is the last tolerance we're going to briefly touch on. The tolerance zone for total runout is two concentric cylinders, and the difference between runout and cylindricity is that runout is located relative to another datum. Because the tolerance zone is the exact same shape as cylindricity, it also controls cylindricity. Total runout is used to control the distribution of mass on a spinning object to make sure it's appropriately balanced. Runout was traditionally measured using a dial test indicator and a special part holding chuck. And while you can still measure runout this way, the GOM Inspect software allows you to use the actual 3D data of your surface to measure runout. There's been a new movement in manufacturing and quality assurance over the last few years to reduce the need to look in separate files or locations for all of the information needed for manufacturing and inspection. The idea behind these standards is to merge the CAD, drawing, inspection requirements, material properties, and everything else into one machine-readable file. Compliant software will then be able to extract the data without the need for human intervention. You'll sometimes hear one of three terms used to describe this. The first is MBD. MBD stands for Model-Based Definition, and again, the idea here is that inspection elements and tolerances are directly connected to the CAD model, and that you do not need a traditional PDF print drawing, but you can still have one if you'd like. PMI stands for Product Manufacturing Information. This is technically part of MBD. However, sometimes you'll hear this term used with MBD interchangeably. QIF is a latecomer to the party. Since it's an open standard, it's being adopted quite a bit throughout the industry. This actually requires a second file in addition to your CAD to hold manufacturing and inspection information. In a compliant piece of software like GOM Inspect, when you bring a CAD file which contains PMI data, the software will automatically construct all of the nominal features and inspections for you. There is no need to manually create each feature and inspection on the part while looking at a drawing. Not only does this drastically decrease inspection time, but it ensures that everyone at all points in the supply chain are measuring the part in the exact same way. Alright, so the project I have open right now contains a hilariously badly printed 3D part. And what I'm going to do is add a CAD file which contains PMI data. Quick note before I do this, if you're using the free version of GOM Inspect, you will not be able to import the PMI data attached to the CAD file. PMI import is a feature only for the professional version of the software, just so you're aware. So what I'm going to do now is grab that part and drag it into the software, and we're going to hit Add to Part. The software is importing the CAD, constructing the relevant surfaces, but it's also creating all of the relevant checks that are embedded in the CAD file. There's a lot of checks, so it takes the software a couple of seconds to do this. And now the only thing I have to do is create an alignment. Align the CAD and the mesh together, and then allow the software to automatically recalculate all of the associated elements and then inspect the part per the standard. And we're done. And we can zoom in and see that several of these features are calculated correctly. You'll notice this one here has the triple question mark. This is because we have a position with MMC, and my guess is the feature of size here is non-conforming. And that's why the MMC check is failing. The software doesn't know how to evaluate MMC checks when the feature of size, the size constraint of the feature is non-conforming. But everything else calculated automatically, as you can see, which means that with all that stuff embedded into the software, everything calculates, which is really cool and really fast. In conclusion, GD&T provides unambiguous inspection plans, meaning that everything is inspected in the exact same way regardless of who's measuring it. Tolerance zones are based on the functional requirements of the part rather than plus-minus dimensions. This means your tolerance zones are larger and more parts are acceptable through inspection, reducing scrap and lowering cost. Advanced inspection suites like GOM Inspect allow you to visually see how your part is performing in relation to GD&T inspections. This allows you to quickly and easily troubleshoot what is going on in the manufacturing process and correct it faster with fewer repeat inspections. And with the use of PMI, it's possible to automatically generate inspection plans and to ensure that these inspection plans are consistent regardless of who performs the inspection or where it's performed. I hope you found this presentation useful. Thank you so much for watching.